Hey, I think we are live now. Hey, everybody. Welcome back to our third day of distance learning. If you are there and you want to say hi, feel free to say hi in the chat. Our goals for today are to continue the electromagnetic spectrum, mainly talking about, hello, Chloe. We're mainly going to be talking about how to do the calculations. I will push my comfort zone and talk a little bit about heat, which is kind of a physical science thing, but we'll talk a little bit more about that. And then kind of tease tomorrow's lessons. Oh, there we go. Our classics. Emily, hello. Ray, hello. Maddie, hello. Veda, hello. Perry9, Sharon, hello. There's Bree. Ryan. No, Connor, I will not join your league. You are simply going to move on to another game. I am on to your shenanigans. Hello, Emily. Oh, that's good. Hey, everybody. That's good. Hey, 20. We'll take who we got. Lena, Lindy. Hello. Hopefully I didn't miss anybody there. Alex, I think I got you too. Madison, hello. And so, without further ado, we'll dig in. I'll try not to make this too long today. What we can do with the electromagnetic radiation is use that as a way to practice solving for algebraic equations. The math in this unit is not much. We don't have to do much with it. But again, we can use it to strengthen our prefixes. You guys all love your metric prefixes. And we can use it to practice some of those other showing work skills. We do have a mailbag question today, though, so I'm excited about that. If you guys have questions that you want to email me or, of course, ask in the chat, if I don't get to it today, I can start the next day with that. So if you, again, send me an email, that gives me time to make sure I get a good answer. And so we do have a mailbag questions today, which is very exciting. Hold on, let me get it together here. And so our mailbag question was, again, so how would you teach the difference between visible light and ultraviolet light to someone who is blind? And I thought that was an excellent question. I had to ponder that over for a little bit. And so really, I think that it would be probably easier for someone who, depends on what you mean by blind. Blind from birth is someone who has never experienced vision, would probably not have that much of a conceptual leap to understand the difference between visible light and the invisible light, since they really have no frame of reference for any of that. So again, if someone had never seen anything before, for you guys, like the difference between microwaves and radio waves and X-rays, like you're pretty accepting of those differences because you haven't seen any of them anyway. So if you were blind from birth and visible light was something that you had never experienced, I think then sort of from a removed sort of view, then the idea of red light versus infrared would not be that big of a deal. Because remember, the only real difference between any type of electromagnetic radiation is the fact that they just have different wavelengths and therefore different frequencies. And as the wavelength gets out of our realm of perception, it still exists. So again, just imagine if the wavelength gets compressed too much, right, then you just can't see it. And if it gets spread out too far, you just can't see it. So I thought that was an excellent question to really understand the difference between theirs. So what we're doing today then, hi Micah, what we are going to be doing today is we're going to review very quickly just the properties of a wave. So let me get this stuff out of here. Remember that we talked a little bit about the properties of a wave yesterday. We talked about the difference between longitudinal and transverse waves. That's not in the video, but I think many of you remember that from maybe middle school. Longitudinal waves are not what we're talking about, not like sound waves or anything like that. And you will see some charts that put sound waves on the same charts as the electromagnetic spectrum just to show the relative wavelengths, but just understand they are different. Remember, longitudinal waves need some kind of medium to transfer through. Transverse waves, like light, do not. So what else did we talk about? We talked about the basics of electromagnetic radiation there. And so there's that stuff. Again, you don't really have to worry too much about that. Just in here, we need to know the difference between wavelength and frequency. Remember that wavelength is the length of a wave, typically in meters, but we will use different prefixes to find a more appropriate unit for the distance we're talking about. And then the idea of frequency, how often it passes a given point. I think the best way of thinking about that is, again, to use the idea of like a tank tread. So if you look here, if you see this tank tread here, if the tank tread is moving, then the longer the wavelength is, the less you're going to see different colors go passing by. And the neat thing about the speed of light or electromagnetic radiation is that the tank treads are always moving at a constant speed. If you're thinking about other types of waves, they might be going by at different speeds. So a wave through air or a wave through water or even a wave on like a slinky or something like that, these are going to have different speeds. But electromagnetic radiation is always traveling at the speed of light, at least in a vacuum. And so it's very easy to think of sort of a constant motion of a tank tread. And again, if you painted wide swaths of that, the longer you paint a certain color, the less likely you're going to see new colors, and that's the idea of frequency. We also briefly yesterday went over the electromagnetic spectrum. I thought this was a neat graph here, and again, there's lots of these all over the internet. The nice thing about this is it does show the relative length in meters. It shows what that would be in frequency, and I'll teach you how to do that calculation today. It shows you some really basic sources of the electromagnetic radiation that we know, and then it shows a nice relative view. I think with this chart, I think the things that if we ever went back to sort of traditional assessment, you would need to be able to place these things in the relative distance. So where does radio waves belong versus microwaves versus other things? So you should be able to place those sort of things on there. Notice that people are here. We do give off infrared radiation because of the vibration of our molecules. We'll talk a little bit more about that today. And of course, here's the sliver of visible light. This is the only part of the electromagnetic spectrum that we can see. All right. And so let's go on here. Again, remember that if you take a look at the electromagnetic spectrum here, part of it is in the visible range and the rest of it is beyond the range. So we have the radio spectrum here, which we touched on yesterday. I think one of the neat things is, again, just notice how we use this. This is just the radio spectrum of the electromagnetic spectrum and how we use it. And so notice how all these are sliced up for different sort of proprietary uses, and I thought that was pretty neat too. So what we're going to do right now is we're going to jump right in to solving some of these problems. Again, so here's an example of a practice problem here. And that's the idea of you're going to be either given frequency or wavelength, and you're going to be solving for the other. Remember that with electromagnetic radiation, we are always dealing with a constant speed, and that constant speed is the speed of light. And so what we're going to be doing here is we're going to be going over that stuff. So let's do a problem here. Let's get our brush out here. I apologize if you see the brush pop in. All right, so here's the kind of problem that you're going to be responsible for. So let's say that we have a type of electromagnetic radiation, and it's got a frequency of 30 petahertz. All right, and so the idea is what would be the wavelength of that, and we'll solve for it first in meters, and then we'll solve for it in other stuff too. And so the thing you guys need to understand is that the equation for this, for the speed of light at least, or for electromagnetic radiation, C equals wavelength times frequency. All right, and remember we talked about that yesterday. Lambda is wavelength and nu is frequency. The cool thing about this is that it's always going to equal the speed of light, at least in a vacuum. The speed of light you can write to whatever number you want. We are going to be writing it to 3 sig figs. That should be enough for what we are doing. 3 times 10 to the 8th meters per second. All right, so always remember what the speed of light is. And so really what we're dealing with is we're dealing with an equation just like any other equation that we have to deal with here. This is no more complex than, for instance, density. So before we do this, let's just real quick show how we would solve for these equations here. So remember that if we have C, let me move this to where we can see it here. Give me a second here. Let me get rid of this stuff here. So real quick, remember that we have the equation C equals lambda nu, right? We can solve for lambda. And again, we guys would get lambda by taking C over nu, right? Or we could solve for nu by getting, again, C over lambda. All right, and this is stuff that we've done before. Remember that we can check these equations by using the units. All right, so as you're solving these equations, just remember we can always use units to check for this stuff. We know, for instance, that c has to equal the speed of light, and the speed is in meters per second. So if we take all these down, right, we should be able to figure out what these units should be. Again, wavelength is going to be in meters. And then, so even if you don't know what frequency is, even if you don't know what the units for that are, then again, you can kind of derive it from this, right? If we have meters per second over here, and we have meters over here, remember that this has to be then whatever per seconds are. And that's what a hertz is per second. So if I take meters times 1/seconds, I get meters per second. And that's how you end up with that, all right? So we can do the same thing with wavelength, right? If wavelength is in meters, right, we can double check that this is the right equation. Remember, c is the speed of light, so that equals meters per second, right? And then it's going to be over frequency, which is per seconds. Now that looks very confusing. I don't like to have fractions over fractions, so one of the things that you can do is you can rewrite this as, remember that when you're dividing, you're multiplying by the inverse, so I can rewrite this as meters per second times, seconds over 1. And again, as expected, we get meters, meters equals meters. If that confuses you, manipulating units, again, just plug numbers in. Remember, if we have, let's say we take 10 and divide it by the fraction 1/2. Okay, well, don't get freaked out about that. We can have 10, and we can change that into a number, right? 10 over that would be 20, right? Or we could take 10 and then multiply it by the inverse, right? And again, we would get 20 either way. So if fractions over fractions are freaking you out, don't really worry about it. I just like to multiply by the inverse, and then you should take care of that. All right. Again, the last thing we can do with this is check out for frequency itself. Again, many of you have probably done this already working ahead. Again, if c equals, whoops. Let me just get rid of that. So if c equals meters per second over per seconds, again, many of you can see that per seconds will cancel out, but feel free to rewrite that as meters per second times the inverse, right? Oh, I'm sorry, we did that wrong. Sorry about that. I got wrapped into my old problem there. There we go. So I have meters per second over meters. Again, we can just rewrite that as meters per second times the inverse, which would be per meter, and those would cancel out. So hopefully you guys understand how to, again, make sure the units are working out for all this stuff. So if we go back to the problem here, right? So if we're solving for this problem, again, what we're going to have to do is we're going to have to convert petahertz to hertz. And that's not a big deal either if you guys remember your factor label prefixes. So let's go ahead and convert that, right? If we have 30 petahertz, all right, you guys all love your metric prefixes, I remember that. And so what we're going to do is we're going to remember that, again, 1 petahertz, right, is going to equal 10 to the 15th hertz. All right, so we're going to end up with, for your math fans out there, 3 times 10 to the 16th hertz. Okay, so that's not a big deal to figure out. Actually, this should probably be a capital H. All right, and so now we're ready to solve this problem. What we can then do is we can then say, okay, well, we know that lambda, right, equals c over nu. And we know that the speed of light is 3 times 10 to the 8th meters per second. And that is going to be over our frequency of 3 times 10 to the 16th hertz, or per seconds. All right, I'm going to erase some of this work down here. I got to make that bigger. Hold on. I'm going to erase this conversion down here so I got some space to work. Now again, the only thing that makes this anything different than like a density problem is the fact that it's just a little bit more intimidating. All right, so obviously 3 over 3 is going to be 1, and then that's going to be 10 to the negative 8th. If I take this out, I'm going to end up with meters. All right. Now again, remember that you can subtract exponents when you're dividing them. That's not a big deal. Or you can run it through a calculator. And so that's all we'd have to do for that. The unit closest to that would be nanometers. And so what I can do is, again, for you guys who love your metric prefixes, we put nanometers on the top. 10 to the 9th nanometers equals 1 meter, right? And then we're going to then multiply that out. So again, fans of math would realize that would be about 10 nanometers. So again, if you have any questions about that first problem, just let me know. But that's the sort of math that you're going to be responsible for exams on this kind of stuff. It's really not that big of a deal to do this kind of stuff. Remember, nothing more complex than the kind of variables that you would see in a density problem. So again, if you have any questions, just go ahead and ask. Again, what did we have to do there? We had to convert petahertz to hertz using metric prefixes. We had to solve for a variable there, and then we just had to make units work out. Scientific notation made it a little bit more complicated, but if you remember your rules for exponents in division and multiplication, it wasn't that bad. Right? So we'll show you one more version of this problem. We will get rid of problem 1, and we'll throw up problem number 2 here. Again, just looking at it from the other point of view. Again, humans give off infrared radiation, and this is considered long wavelength infrared radiation. By the way, if you're at all interested in electromagnetic radiation, there are tons of resources out there to learn about each type of the electromagnetic spectrum. It's actually really fascinating. So if you are looking to better yourself and learn a little bit more about any of this stuff, X-rays, microwaves, any of that stuff, all of them could be done. There are entire lessons about every single one of them. All right, so hopefully that bought you a little bit of wait time to get started with this practice problem if you wanted to get started with it. And so what we're going to be doing is just solving it from the other point of view. Obviously, I could give you wavelength and frequency, and you could be making sure that the speed of light is working out. That's a pretty straightforward problem here. So hopefully you've sort of worked ahead. So I will, again, write down my relevant information for this problem. Let's use a different color just so it stands out a little bit. All right, so here we go. Let's put our relevant information down. We have a wavelength, right, of about 10 micrometers, okay, and we're going to have to convert that. What is the frequency of that? Again, we know that c is the speed of light in meters per second, and you can use more or less sig figs as much as you'd like to. I would encourage you to work ahead and figure this out. So let's just go ahead and convert this. Again, a micrometer, we know that there are 10 to the 6th micrometers in 1 meter. So when we do that math, we're going to end up with 1.0 times 10 to the -5th meters. And that's going to be our wavelength. That's about the size of the infrared radiation that you give off. And then we're just going to be plugging it in. Remember, we know the equation C equals lambda nu. Again, feel free to work ahead and make sure that you're getting the answer before I do. And then we're going to solve for frequency this time. So we're going to isolate frequency. Frequency equals C over lambda. And so that's going to be 3 times 10 to the 8th meters per second over our value of 1.0 times 10 to the -5th meters. Again, I will skip the idea where we figure out what the units end up being, but most of you guys could realize that meters per second over meters is going to cancel out to per seconds. And so we are going to end up, now again, if we have 10 to the 8th over 10 to the -5th, we essentially add those exponents. So we're going to end up with 3.0 times 10 to the, if I remember correctly, 13th per seconds, or hertz. And again, fans of prefixes will know that, again, we can probably translate this to tera, which is right around that. So we're going to put 10 to the 12th hertz on the bottom, and then we'll put 1 terahertz on top. And so that ends up being about 30 terahertz. Okay, and so that is the frequency of the electromagnetic radiation that you give off. Yeah, Alexandra, that's a good question. If I don't ask for a specific unit, then I would just leave it in meters. I mean, make it easy on yourself. I will probably, on the test, ask for it in a specific unit, like terahertz or something like that. I probably wouldn't say find a nearby unit and convert it to that. That's a little bit too loosey-goosey for my taste. But again, if they don't ask for a unit, just whatever unit the problem cranks out, I would put it in that. And otherwise, I'll tell you what unit it is. Again, tera is a little bit outside the units that we typically used, so I probably wouldn't worry too much about that. But that was a very good question. So is frequency determined by wavelength? That is also a very good question. Yes. So given the fact that it's electromagnetic radiation, we know that C is a constant. So if it's electromagnetic radiation, we're going to assume it's traveling in a vacuum. And so if I give you the frequency, you therefore know the wavelength. And if I give you the wavelength, you therefore know the frequency. So that was a very good question too. And that's it. I mean, that's really sort of the math that we're going to deal with this. The only thing really left is the idea of really then finding the energy of stuff, but we'll talk about that later. As you go forward in the lessons, if I go over really any other equations, like you'll see me talking about like relativistic mass in the next lesson or in the next couple of lessons, you can pretty much ignore that math unless you enjoy just seeing how the units work out. And then again, there'll also be a point where we find like the wavelength of an electron. Again, that's just for the people who enjoy math and sort of figuring out units and things like that. But if we were to have a traditional assessment on this material, it's really going to be, again, frequency, wavelength, and then we'll show you the energy equation later. So those are really good questions. I appreciate that. All right. So going forward then, here's this one thing. And again, I'm kind of pushing my comfort zone here. But one thing that we should probably think about is, since we're talking about this stuff, hold on, let me clear out some of this stuff here. Let's talk a little bit more about heat itself. And again, this is pushing my comfort zone a little bit, but one of the things that we need to understand is that infrared is a type of thermal radiation. It's part of the electromagnetic spectrum. That's something you guys need to understand. Infrared is often called heat radiation, but that's a little bit of a misnomer. There are lots of different types of electromagnetic radiation that will heat stuff up. In fact, a lot of the heat that we get here on the planet Earth, yes, some of it is infrared radiation from the sun. And again, infrared thermal radiation doesn't need a medium to transfer. That's why, again, the sun can heat us up with infrared, because infrared is what's called thermal radiation. It doesn't need a medium to transfer through. It's a transverse wave. But a lot of the other types of electromagnetic radiation that reaches the Earth, when it's absorbed by the Earth's surface, is re-radiated as heat, as IR. So it's just sort of a coincidence that we sort of exist in this range where thermal radiation and IR are about the same, but lots of electromagnetic radiation can heat stuff up. So sort of keep that in mind. And again, don't worry about this if you don't find this part interesting. It's not really, this is sort of enrichment more for us. But just remember that, again, energy, really any kind of flow of energy is known as heat. And then heat will essentially flow between any two adjacent systems until they're at thermal equilibrium. Remember, we talked a long time ago about the idea of what temperature is. And temperature is sort of that weird measurement of the kinetic energy of molecules in a system. So again, molecules are kind of like vibrating and rotating and things, and we call that sort of like temperature. And if you put things next to each other, they want to transfer that. So there are other ways of transferring heat besides what we call thermal radiation, infrared. You are radiating, the molecules in your body are vibrating, and you are giving off thermal radiation in the IR range. But that's not the only way that we transfer heat. There are physical ways of doing it too. And again, you might have learned about that in middle school. There's conduction, and that's the idea that the energy is actually being transferred between the bodies. So you're touching something, and then the heat energy from you flows directly into that object. You lose heat energy, it gains heat energy. That's conduction. And then there's convection also. If you think of a convection oven, fluids in motion can actually carry the heat from place to place. So if you heat something up and then that water moves, the water molecules are carrying the heat to a different location. So there are different types of ways that heat transfers. Don't freak out about that. Again, we're probably not going to test you on that, but what makes thermal radiation different than convection or conduction is that, again, it doesn't require a medium. It's electromagnetic radiation. So yes, your molecules are vibrating and they are giving off electromagnetic radiation, but they're also vibrating and then transferring heat to nearby things. And then also, if you heat the air up, the air can then move and take the heat with it. For those of you who are really enjoying this deep dive into heat, and I don't know how many of you are enjoying it, there is a property called emissivity, and that's, again, how well you actually transfer heat, from thermal radiation. So you, I think, have a thermal emissivity of about 1. And so most of your energy is then thermally radiated, but some things have a much lower one, and those would be things that we don't want them to lose the thermal energy. Sort of like, I think solar panels are a lot like that. So anyway, some advanced notes for you in case you care about, there are different types of ways to transfer heat. For those of you who are interested, feel free to dive a little deeper. You will see more of this, I think, in physics as you go on, but, in case you care. All right. And so really, I think the last thing we really need to do here is, let me get rid of all this stuff, is just talk about where we are taking this information going forward. And that's the idea of Max Planck and the idea of the modern view of the atom. So again, when we last left atomic theory, we were dealing with the planetary model of the atom. And that's the idea of we have a nucleus in the middle, and that the electrons are orbiting around it like little planets. And that explained the evidence from like the gold foil experiment, but classic physics was having problems explaining what this all meant in terms of just the way classical objects move around things. Like, it didn't really make a lot of sense. And so what we had is problems at the beginning of the 20th century about, well, how are we going to view atoms going forward? There was a couple unanswered questions, and we'll talk more about this tomorrow, but we had the problems, again, of just the bright line spectrums. Again, we have been talking about bright line spectrums for a long time. We know that every element gives off its own bright line spectrum. And classical physics really didn't have a way of explaining that. People found pneumatic patterns to where these bright lines came from, but these bright line spectrums were going to be a big clue about figuring out how atoms actually exist and how atoms actually work. And the other thing that we are going to touch on tomorrow, and we're going to do a very simple explanation of this, is the thing that Planck was really trying to deal with, and that's the idea that one of the things we saw at our realm of existence is the way things gave off energy, which is called black body radiation. You guys all remember in the laboratory, when we heated stuff up enough, stuff glows. So, if you have a piece of wood in your fireplace, at some point it starts to glow, right? And that is the energy being given off because of that higher temperature. And then the same thing goes for any object, whether you heat up a ceramic pot or a piece of wood or bone or anything like that. Once it gets hot enough, it starts to give off colors. And that was a big problem for classical physics. What we saw in the real world, and you can see over here, and again, you don't have to worry too much about this graph, is that as we heated objects up, they gave off certain colors. But that is not what the science predicted. And science predicted that, based on how we knew of stuff, that if you heated stuff up, it would start giving off more and more energy, and then eventually things would become invisible. They would be giving off essentially nothing but high energy ultraviolet light. And so obviously that didn't happen. Like, things remain visible when you heat them up. And that is the lowest, simplest explanation that I can give about what was called, and I love the name, the ultraviolet catastrophe. So this is what Max Planck was dealing with, and this is what we're going to be talking about tomorrow. And this is going to really give birth to the modern view of the atom, the creepy, weird, but realistic view of the atom, where things don't really make sense based on our classical view of atoms. But Planck realized that our view of matter was wrong, because when things glowed, we could still see them, and physics couldn't explain that. So that's sort of our teaser for tomorrow. I encourage you, if you are interested in learning more about this, as opposed to just the video, on the weekly assignment sheet, I gave lots of links to some of the deeper dives into Max Planck and the ultraviolet catastrophe and Planck's constant and some of the stuff we are going to talk about tomorrow. Remember, don't freak out too much about this stuff. We are going to start with a very, very simple explanation of this stuff. So I know it's going to sound kind of weird and intimidating. Don't worry about it. I'm only a little ahead of you on this stuff. And so what we will do is we will talk about a very basic introduction of what Planck thought was different. And which is challenging because, again, you guys haven't really thought about this stuff anyway. So that someone's saying that something is different than something you never thought about before, it doesn't really matter. So please watch the video for tomorrow. If you have questions, obviously email me or post them in the comments to this video, and I'll try to get back to them tomorrow. And so that's it. That's pretty much what we are going to be doing for today. If you would like, I will, of course, do a picture of the day. Some of you guys enjoyed that. So if there is a picture in the chat, I will do a picture in the chat before we go. If somebody would like to request something, I will do that. Otherwise, if you are done, you can take off. Let me see if I'm ready here for art. I am ready. So I will do one artistic request if there is anybody left in the chat. A bird. I can do a bird. That's easy. That's good. I like that. I can do a bird. All right. A bird with hand sanitizer. All right. We'll do like a little improv here. All right. So we'll do, let's see. We'll start with the hand sanitizer here. Remember, guys, soap works just as well. A lot of people forget that. You're like, is that the bird or is that the hand sanitizer? Yeah, if you just wash your hands 20 seconds, really with soap, that's fine. Although the hand sanitizer is great if you're out and about. But remember, you should not be out and about. Right. So there's some hand sanitizer there. Right, and then, so we'll draw a bird here too. Let me think about how this is going to work. We'll draw the bird a different color. All right, let's just kind of improv here. So he'll have his little wing on there. Oop, he got a little out of proportion here, but no going back. Do, 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 do. Ooh, do, do, do. There's a bird with hand sanitizer. And we'll give him a pot pie hat also. There you go. Hey, thanks. I appreciate that. That was fun. All right, so for tomorrow, look at the Max Planck notes. And again, I'm still working on assessments and things like that. I appreciate you guys tuning in. And I think that's it. So be safe. Continue your social distancing. Thank you for the requests. And if you have any other things, we'll answer them in the mailbag tomorrow. Thanks for watching and have a great day. And again, please post your questions if you had them. I will try better explanations tomorrow. All right, see you guys.